In this video, we're going to cover how to take the derivative of inverse functions. But first, let's review what an inverse function looks like. Hopefully you can recall from pre-calculus, if you're given a function, how to find its inverse function and how to graph that. If you recall, if you're given a function f of x, here it is, the inverse function is just a mirror image about the line y equals x, isn't it? And so the inputs or the x values for the original function correspond to the y values for the inverse function, and the y values for the original function correspond to the inputs or x values of the inverse function. So here we have a point, this point right here, corresponds to f inverse of a is our x value, and the y value is a, and then on its inverse function, notice that they're switched, and here we have the x value is a, and the y value is f inverse of a. What we've done here is we've added a tangent line at that point. So we've added the tangent line to f of x at the point f inverse of a, and its corresponding tangent line to the inverse function at the point a, f inverse of a. And notice that those are also mirror images of one another about the line y equals x. The slope of this line, which we the notation for that is f prime, right? The slope of the tangent line is just f prime at the x value. So f prime at f inverse of a is just q over p. It's the rise over the run. All right, so we have q over p. And then the slope of the tangent line of this tangent line, which we could denote f inverse prime of a, so it's at this point a, f inverse prime of a, is actually the reciprocal, or p over q. This is just a reciprocal of this, okay? Now, when we say reciprocal, remember, if we take the reciprocal of 5, it's just 1 over 5 as the reciprocal. So if this is just the reciprocal of this, and we can think of it as 1 over q over p. So let's look at this equation at the top. This is telling us that f inverse prime of a, which is this value down here, f inverse prime of a, is just equal to 1 over, remember, the reciprocal of this. So that's f prime of f inverse of a. So this is our equation, and it works for all a values where f prime of f inverse of a does not equal 0. We can't have that denominator being 0. So this is basically how we came up with the rule for the derivative of the inverse function, which we're going to see next. There's a lot here, but I'm going to boil this down for you. It says, let f of x be a function that is both invertible and differentiable. That means that the derivative exists everywhere along the domain, and also that you can find the inverse function of f of x. If that's the case, and g of x is the inverse of f of x, then g prime of x is equal to 1 over f prime of g of x. Okay? And that's only if f prime of g of x does not equal 0, right? We don't want that because we can't have a 0 in the denominator. So let's go ahead and look at an example. The example says, given f of x equal to the quantity x plus 1 squared, we want to find f inverse prime of x at x equals 9 in 2 different ways. All right, we want to find f inverse prime of x. We want to find the slope of the tangent line to the inverse function at x equals 9, and we want to do it in 2 different ways. So let's do it the way that we would do it before we knew this theorem. Before we knew this theorem, we would have solved the problem by finding the inverse function and then taking the derivative of it and plugging in x equals 9. So let's do that first. If we're given f of x equals x plus 1 squared, all right, we can rewrite that as y equals x plus 1 squared. And we want to find the inverse function. Remember how we do this. We swap the x and the y, and then we solve for y. So to solve for y, I'm going to take the square root of both sides. So I get the square root of x equals y plus 1, and then y would equal the square root of x minus 1. And then that's my inverse function. If I wanted to take the derivative of that, I would rewrite this. I could rewrite this as x to the 1/2 power minus 1. The derivative would be 1/2 x to the negative 1/2, and then the derivative of negative 1 is just 0, which I can rewrite as 1/2 times the square root of x. And we want to find that at 9, so I'm going to, instead of calling this y prime, I'm going to call this f inverse prime, and we want to find that at 9, and that would give me 1/2 times the square root of x, or the square root of 9, which is equal to 1/6. Okay, so that's our first way of doing it. Let's do it now using this theorem. The theorem says that g prime of x, so g is our inverse function, and g prime of 9 would equal 1/f prime of g of 9. All right, so we're going to need f prime of something. So let's go ahead and take the derivative of f of x. F prime of x would equal 2 times x plus 1 to the first power times 1. So that would just give me, I'm going to distribute the 2, and I'm going to get 2x plus 2. That's my f prime of x. Now, we're going to have to find f prime of g of 9. So we have to find a value for g of 9. And how do we do that? So remember what this means. This means this is my x value in my inverse function. And if I'm looking at the x value in my inverse function, that was the y value in my original function. So 9 was the y value in my original function f of x. So what I'm going to do is I'm going to plug 9 in for f of x here, and I'm going to solve for x. All right, and the way I solve for x is I take the square root of both sides, so I get the square root of 9 is going to be 3 equals x plus 1. So what is x equal to? X is equal to 2, isn't it? Subtracting 1 from both sides gives me x equals 2. So I'm going to find 1/f prime of 2. And what is f prime of 2? Well, here's f prime of x. So if I take f prime of 2, it's going to be 2 times 2 plus 2. So that's 4 plus 2 is 6. And so g prime of 9 is equal to 1/6. And notice that I got the same answer doing it both ways. So which of these ways is easiest? Well, in this case, both ways were pretty easy, right? Finding the inverse function was quite easy, and so we could have done it that way. We could have done it this first way with no problem. However, there are times when finding the inverse function is quite hard, so it's easier to use the method that we learned here with Theorem 3.11.